so with more complex designs, where we have more than a single independent variable, we're going to have a number of different conditions in experiment, quasi-experiment, or even correlational study. And the number of conditions that we have can get quite large fairly rapidly. If you think about the situation that I was talking about earlier with the visual search experiment, we had two variables that each had two levels. So set size had size 6 and size 12, and the type of search was either conjunction or feature. So we have two levels of two variables. So how many total conditions do we have? Well, all we need to do to find the number of conditions is just multiply the number of levels for each of the variables that we have. So 2 times 2 equals 4. So we had 4 total conditions, right? We had feature search at size 6, feature search at size 12, conjunction search at size 6, and conjunction search at size 12. Now, there's an interesting consideration that we need to think about, and it has to do with balance. Balance is crucially important when we're talking about methods design. We use statistical methods to balance out different things, right? So when we are taking a number of individual trials to see how I perform in some condition, what we're doing, we're taking a mean in order to balance out the times that I'm paying more attention with the times that I'm paying less attention. The times that I am more fatigued with the times that I'm less fatigued. The times that I have less practice with the times that I have more practice. Speaking of practice, there's something else that happens in a lot of laboratory experiments. So practice can have big effects on people. So what happens in a lot of experiments is subjects will actually be given a block of trials. So a block of trials is just simply a number of trials. And that first block of trials is often considered practice. So participants get a little bit of practice before they actually are participating in the test data that the experimentalists are going to analyze. So often that practice is not contained in the final analyses. But anyway, so you take a mean of all of my trials in the test trials to balance out the more and less distracted whatever, to get a better indication of how I perform in that particular condition. You take means of a number of subjects to get a better estimate for how people in general perform in that condition. And if you've done things properly, you've randomly assigned people to different conditions. If you're doing between subjects designs, if you're doing within subjects designs, every participant is doing all the conditions, so you don't need to worry about random assignment to conditions. However, the order could be a big player. So it's possible that doing a task, let's say I only was doing the search 4 times. If I had done the most difficult search, the conjunction search with set size 12 first, this might make the later searches much easier for me. So having that particular order could influence how I participate later. So if we think about order, what's going to determine how many different orders that we have? Well, the number of conditions was just the number of all the independent variable levels multiplied, right? 2 by 2. So this is the number of conditions. The number of orders, or the number of possible orders, is going to be the number of conditions factorial. So that's factorial and not an exclamation point. So in the situation where we have 2 independent variables with 2 levels, we have 4 total conditions, and we are going to have 4 factorial orders. So 4 factorial means 4 times 3 times 2 times 1. So this is 4 times 3, that's 12, times 2, that's 24, times 1, that's just still 24. So even with a very, very simple design, right, 2 variables with 2 levels each, You can't get simpler than that unless you just go to a single independent variable with 2 levels. Or I guess you could do a single independent variable with 3 levels. But regardless, like, that's the simplest complex design that you can have. And you have 24 different possible orders that people could participate in. In one of my graduate school projects, I had a situation in which I had, let's see, I've got it over there so I can refer to this more easily. I had 1, 2, 3, 4, 5. I had 5 different variables. And the different variables had 8 times 3 times 2 times 2 times 2. So 5 independent variables. One had 8 levels. One had 3 levels. One had 2 levels. Another one had 2 levels. And finally, the last one had 2 levels. So in this situation, there are 8 times 3, that's 24, times 2, that's 48, times 2, that's 96, times 2, that's 192 conditions. Wow, that's a lot of conditions. How many different orders do we have? Well, that's 192 factorial. And on R, which I like to use for running statistical analyses, R can't even compute the value of this. R can compute the value of 170 factorial. And amazingly, 170 factorial, where's my note, is equal to, or roughly equal to 7 times 10 to the 306. So this is basically 7 followed by 306 zeros. That's a big number. That's a really big number. That's more than the number of atoms that are expected or that are predicted to be in the observable universe. So the number of atoms that are thought to be in the observable universe is just 4 times 10 to the 81. So that's 4 followed by 81 zeros. So in my graduate school research project, I had potentially, well, I did, not potentially, I had more possible orders that I could run than there are atoms in the universe. So there would really be like, no way that I could conceivably do that in a multitude of lifetimes. So what do we do? How do we balance order effects? Well, there are a number of ways that we can do it. If we just have a small number of conditions, then doing complete counterbalancing isn't that big of a deal. So counterbalancing refers to doing something that is going to weigh one effect or balance one effect with some other effect. So the idea is that the effect of having one condition first is balanced by having another condition first. And in complete counterbalancing, basically we would have every possible order of conditions. So if I wanted to do an experiment with complete counterbalancing and I had a 2x2 design, I would have to have 24 participants. So 24 participants is actually a fairly small number of participants when it comes to psychological research. There are some projects that use hundreds of participants, or even like epidemiological research where you have hundreds of thousands of participants in some cases. So 24 is really a small number. I often do experiments where I have less than 24 subjects. And I'm able to get really powerful results. Why is this? Well, I use experiments where I'm manipulating the variables. I use repeated measures within subjects' design so I can get rid of variance, and I can also break variance into tiny pieces. Another thing that I do is I gather a number of observations for each of my participants. So rather than just getting one data point for one participant, I gather maybe 20 data points for that one participant in a single condition. So I can take a mean of that and get a really great idea about how they perform in that condition, and avoid a lot of the other types of variance that would be a problem if you only have a single observation for a single individual. Anyway, so complete counterbalancing, it's a hassle. If you've got a reasonable number of variables and a reasonable number of levels for those variables, things get messy very, very quickly. We'll refer to the number that you would need to have to completely counterbalance things as we go through a couple other examples. Now, another solution to some order effects is to use a Latin square. So in a Latin square, we're going to have one order, so one participant's going to perform in condition 1, 2, 3, 4. The next, or some participants are going to perform condition 2 first, 3, 4, then 1 last, and so on and so forth. And what you notice about the Latin square is that each number appears in each location. So we have 1 first, we have 1 second, we have 1 third, we have 1 fourth. We have 2 first, second, third, and fourth. And we have 3 first, second, third, and fourth. Same thing with 4. So we have each condition in each position, which is great because it means that we don't need to worry about effects of having a particular condition in a particular position because everything's balanced out. Now there's a problem that you might notice here. With 4 conditions total, condition 2 is always following condition 1 except for in one situation, right? And that is right here. So here, 2 follows 1, here 2 follows 1, here 2 follows 1. If we had 5, 6, 7, 8, 2 would follow 1 there, and there, and there as well. The only place that it doesn't is in this situation here. So this means that we don't have balance in terms of what task follows something else. This is a problem. So complete counterbalancing doesn't have this problem because we're using every single order that there is. But complete counterbalancing, it's almost impossible to do unless you have a tiny number of variables with a tiny number of levels. So, what's the solution? What else can we do besides Latin square? Well, imagine instead of 4 conditions, we had 8 conditions. So if we have 8 conditions, we would need 40,320 different orders to cover all of the possible orders. But we can do something else. Now, Latin square, we could have 8 orders like we did before, but that's going to have the problem where 1 is almost always followed by 2, 2 is almost always followed by 3, and so on and so forth. However, if we do something tricky, we can create a balanced Latin square. So here I'd like you to notice a couple things. Here, 1 appears in the first location, the second location, the third location. Sorry, I just circled 2. Third location, the fourth location, fifth location, sixth location, seventh location, eighth location. Let's see if this holds out for 2, and I'll let you figure out the rest. So 2 appears in the first, second, the third, the fourth, the fifth, the sixth, the seventh, and the 8th position. So again, we have each not each order, but each condition appearing in each possible location. That's great. So we've gotten rid of any effects that have to do with a particular condition, or not getting rid of any effects, but we've balanced out the effects of any one condition being in any particular location. We've also balanced out which things follow other things. So here notice 2 follows 1, but here 4 follows 1. Here 6 follows 1, here 8 follows 1, there nothing follows 1, here 3 follows 1, here 5 follows 1, and here 7 follows 1. So if we take a look at this, notice 2 follows 1 one time, 3 follows 1 one time, 4 follows at once, 5 follows at once, 6 follows at once, 7 follows at once, and 8 follows at once. Let's take a look at what follows 7. So here 4 follows 7, here 6 follows 7. There, nothing follows 7. Here, I should do this in a different color. This is going to be really hard. That's not a great color, but there we go. So let's take a look at our 7s. 1 follows 7, 2 follows 7, 3 follows 7, 4 follows 7, 5 follows 7, 6 follows 7, 8 follows 7. So in a balanced Latin square, not only do we have each condition appearing in each possible location, we also have each condition following every other condition equally often, which is really beautiful. Now, this looks fairly complicated, and you might be wondering how on earth did I do this? Or how could you do this? And it's actually really quite simple. The one caveat is you need to have an even number of conditions. If you don't have an even number of conditions, there are some things that you can do, but I'm not covering them here. So I want you to notice just this top row. If we look at it, we have 1, 2, 8, 3, 7, 4, 6, 5. The pattern might not seem apparent, so let me show it to you. 1, 2, skip 3, skip 4, skip 5. Then go backwards, 6, 7, 8. So the way that I created this was fairly simple. I just went 1, 2, I left this blank, 3, left a blank, 4, left a blank, 5, 6, 7, 8. If you think about this in terms of numbers, it's going to be 1, 2, n, 3, n minus 1, dot, dot, dot. Something like that, where you are going through all of the potential numbers that you have, all the way up to some even numbered n. Now, let's go back to my experiment, because the experiment where I have 192 conditions, there would be 192 orders if we were using a balanced Latin square. And that's still a ridiculous number of orders, especially if we wanted to have one participant each do a different order. So, as I said, I often do experiments with less than 24 participants. I forget how many participants I had when I had 192 conditions, but I'm almost positive that I had less than 36. Lots of times I'd finish an experiment with like 16 participants. So I wouldn't be surprised if I used somewhere between 16 and 36 in that situation. So what did I do? 36, like none of the numbers add up to 36. So how did I design my experiment? Well, if you think about some of the things that we've talked about earlier, we have used statistical controls to control for things, right? We use random assignment to ensure that both groups are statistically, or should be statistically, equivalent with one another, right? We can demonstrate, we can prove, because this is mathematics, that in the long run, that those two groups will be identical to one another. We use random selection to ensure that our sample accurately represents the population. So if we have a population of orders, we can randomly sample from those orders in order to make sure that our sample of orders represents, or is a reasonable representation of the population. So when we do this, it's known as randomization. So we have a whole bunch of different conditions. Which order are you going to get it? Well, I'm going to have a computer determine an order for you. I'm going to have them pick out one random order. Then I'm going to have another participant, and they're going to get a different random order. And something that's interesting, so in this situation where I had 192 different conditions, I actually had participants do each of those conditions multiple times, because each trial was only taking a second or two. So I could, within a single hour, have them do all 192 conditions, actually several times, in different orders, within an individual participant. So that really gives me a lot of strength, not only in honing in on what their true value is for each condition, but it also allows me to reduce the likelihood that I have order effects.